Good morning. Today we are going to discuss about Thevenins theorem. It states that it consisting of a number of voltage sources and resistances can be replaced by an equivalent network having a single voltage source called Thevenin's voltage V Thevenin and a single resistance called Thevenin's theorem or Thevenin. Here, the voltage source has been represented E. There are three resistors has been connected in the circuits R1, R2, R3. Then RL is nothing but the load resistance. Consider a circuit as shown in the figure. Let E be the EMF of the cell having its internal resistance R is equal to 0 and RL is nothing but load resistance that has been connected across AB. To find V Thevenins, that is Thevenin's voltage, the load resistance RL has been removed in the circuit. The current I in the circuit has been represented by I is equal to V by R. Here the R1 plus R2 resistors has been considered as series manner because this is an open circuit. So the I is equal to E divided by R1 plus R2. The voltage across AB is equal to Thevenin's voltage V Thevenin. Then V Thevenin is equal to I into R2. Here the AB has been connected parallel across the R2. So the voltage drop across R2 is nothing but the voltage drop across AB. So by multiplying the current into IR2, we are getting the V Thevenin voltage. So by representing the value formula for current I over here, so I is nothing but E into R1 divided by R1 plus R2. So V Thevenin will becomes ER2 divided by R1 plus R2. To find R Thevenin, the load resistance RL is removed, the cell is disconnected and the wires are short circuited as shown in the figure. The effective resistance across AB is equal to Thevenin's resistance R Thevenin. Therefore, the R Thevenin is equal to the resistance R3 plus these two resistance has been considered as parallel manner. So R1 R2 divided by R1 plus R2. So R Thevenin is equal to R3 plus R1 R2 divided by R1 plus R2. Here R1 is parallel to R2 and this combination in series with R3. If the cell has internal resistance R, then V Thevenin is equal to ER2 by R1 plus R2 plus R. The denominator we have to add the internal resistance small r. And R Thevenin is equal to, instead of R1, we have to represent R1 plus R divided by R1 plus R plus R2 plus R3 as it is as usual. So we have to add small r along with the capital R1, that is nothing but internal resistance of the voltage source. Then proof of Thevenin's theorem. Consider network as shown in below. Here R1, R2, R3 resistance has been represented here. The current I is flowing from the voltage source. At the point here, the current has been considered as I dash. It is flowing through the load resistance RL. The equivalent resistance has been given by the V Thevenin across the parallel RL and R Thevenin. This is nothing but an equivalent circuit of the Thevenin's theorem. That is, R Thevenin has been connected in series with the V Thevenin and RL has been connected across with the voltage source. The effective resistance of the network in one is R3 and RL in series and the combination is parallel to R2, which in turn is in series with R1. This effective resistance has been represented as R1 plus R2 parallel R3 plus RL has been considered as series. So this R1 resistor along with parallel combination of R2, this two will be considered as series, that is R3 plus RL. These two has been connected parallel with R2 and the resultant value has been connected in series with R1. The current I in the circuit is capital I is equal to E divided by R effective, that is capital E divided by, we are substituting the value of R effective from 1. The R effective is equal to R1 plus R2 into R3 plus RL divided by R2 plus R3 plus RL. Therefore, the current I has been represented here. We are taking the complex, the denominator LCM, and we are getting this R2 plus R3 plus RL will be multiplied along with E, and we are having R1 into R2 plus R3 plus RL plus R2 R3 plus R2 RL. The current through the load resistance I dash is found using branch current method. Therefore, I dash is equal to I into R2 divided by R2 plus R3 plus RL. Substituting I from equation number 2 in the equation number 3, we are getting, instead of I, we are substituting this value, and the I dash equation has been represented here. Or else, I dash has been represented by ER2, this R2 plus R3 plus RL has been divided by downside, so these two will get cancelled each other. We are getting E into R2 divided by R1 plus R2 plus R1 R3 plus R1 RL plus R2 R3 plus R2 RL. This has been represented as equation number 4. Therefore, the Thevenin's voltage VThevenin is equal to ER2 divided by R1 plus RL. This is nothing but equation number 5. Therefore, Thevenin's resistance R Thevenin has been represented as R Thevenin is equal to R3 plus R1 R2 divided by R1 plus R2. It has been represented by equation number 6. Consider the equivalent circuit. Second diagram, circuit 2. The current I double dash is the equivalent circuit is I double dash is equal to V Thevenin divided by R Thevenin plus RL. Thank you.